Hello, in this video we're going to talk about second order reactions and their half-lives, and then I'm also going to include zero order reactions even though they're not in your book because I think it's a useful thing to talk about. Alright, so we're talking about overall second order reactions, and so this could either be if you have second order in A, or if you have first order in A and B, and then it's overall second order. We're going to talk about the first version here because the math's a lot easier. So, alright, A goes to B with some stoichiometric coefficients. Now the differential rate law for this is going to look like it does. This rate is equal to Ka squared. Now, the integrated rate law, alright, we're going to move the A to the left, the time to the right, and integrate with respect to A on the left and time on the right, and we get this result. Okay. Now, from here, you can do a couple different things. One, you can rearrange it to get a linear form, and this is pretty much what you'll see on the info sheet of your exam. And so now this shows you that if you plot 1 over A as a function of time, you have a straight line with a slope of positive k. And then 1 over A naught is your intercept. Cool. The other thing you can do is rearrange this to solve for the concentration of A at some time, and then plot that, and then that gives you the concentration as a function of time, and it has this kind of general shape. Alright, so now just add this to your pile of equations. The integrated rate law for a second order reaction looks like this, and we typically will give you the linear form on a test. Alright, so now let's talk a little bit about what if you have first order A, first order B, and it's overall second order. So generally we skip that in general chem because the math here is tricky and I don't think it's worth getting into it. You don't learn as much from it as you need to justify the math. And so often what you can do to investigate these types of reactions experimentally is set up the conditions so you have a pseudo first order reaction where you have one reactant with a much higher concentration than the other, and so over some change in reactant concentration, you can assume that the change in A, for example, is much, much smaller percentage-wise than your change in B. So in effect, A doesn't change over the reaction, whereas the concentration in B does, and so you can pretend that this is first-order kinetics. It's not a bad assumption. It's not particularly great. It's a way to do these experiments in Gen Chem given the types of kinetics we cover. Your rate constants are different if you do a pseudo first order reaction versus, any sort of second order reaction properly, and that's okay. Now let's practice this. So again, you have your equation. This is the form that you have in the info sheet. And so, all right, here's the equation, here's a rate constant. How long is it going to take for the concentration to go from 0.62 molar to 0.28 molar? And so let's plug numbers in, right? Concentration of A at time is 0.28, A naught is 0.62, and then the rate constant goes in here too. Now, here's how you solve it. And then you get out of this that the time is 3.6 seconds. So just like we saw with the integrated rate law in first order reactions, same thing here. Plug numbers in, you can find the information that you want to find. Okay, so let's also talk about zero order reactions. And we'll, again, limit our discussion to a single reactant. All right, so here's what the differential rate law looks like. Rate is equal to K times concentration of A to the 0. Now, we can integrate this just as well. And when we do that, we get this result. Now, there's only a linear form for this because zero-order reactions are linear. And so we can plot this with a y equals mx plus b kind of setup. And so on our y-axis, we have just the concentration of A, and the x-axis is time. And when you do this, you get a slope that's negative k. So zero-order reactions are not as common, but they're still worth talking about, I think. And so an example when you would have a zero-order reaction is say you have some catalyzed reaction where the reaction happens on a solid surface. And these are pretty common in chemistry and industry. And so your kinetics are going to depend on the molecules absorbing, reacting, and desorbing from this surface, of which there's a limited surface area. And so your reaction rate's not going to depend on the concentration. It's going to depend on the surface area of your catalyst. And so that's a zero-order reaction, and you'd have this kind of setup. So again, add this to your list of equations, and we can just go from there. Now, one other thing I want to say is you can do this same whole kinetics thing with a gas and treat it in pressure instead of molarity. So, all right, here's an example. You have the nitrogen dioxide gas, and it makes nitric oxide gas and oxygen. And here's the rate for that. Just the same way we've talked about it before, right? Negative half times the change in concentration of this reactant. And this can also be equal to a half times the production of NO, equal to the production of oxygen. Okay, right, but we'll just talk about the reactant here. Now, let's think about a gas. So we want to talk about concentration because, when we do this before, we have the concentration of our reactants. And so, well, for a gas, you can talk about concentration as well. It's just something we don't do very often. But concentration is just stuff per volume, particles per volume. And, we do this in moles over liters. But to phrase this in terms of the ideal gas law, here's moles, here's liters, volume, okay? Now, PV equals nRT. Let's rearrange this for N over V, because that is concentration, and then play with that, right? So molarity is N over V, and then 1 over RT times the pressure. Great. So we can just take this and plug it in, right? Take this pressure, plug it in for the molarity, for the concentration, and use that as our rate, right? So rate is negative a half change in concentration. Rate is also negative a half times 1 over RT times the change in pressure. And so you can do this. In effect, you can just replace concentration with pressure and realize that your rate constants will be a little different because all of this like inverse RT stuff will get absorbed into your rate constant. But other than that, this works great. You can just use pressure instead of concentration, and it all works out. All right, so let's summarize now that we've talked about integrated rate law for our different reactions. So when you're in the lab collecting data, you typically would measure concentration as a function of time through absorbance or through something else. And so in a zero order reaction, you'll get a straight line when you do that because the concentration doesn't influence the reaction rate at all. And in a first order reaction, you'll get this kind of curve. A second order reaction, you'll get a different kind of curve. Okay. Now you can make linear forms of all these equations as well, right? So for a zero order reaction, it is linear. For a first order reaction, if you plot the natural log of A as a function of time, then you'll get a straight line with a slope of negative K. If you have a second order reaction, if you plot 1 over the concentration of A as a function of time, then you'll get a slope with a positive K, or the slope that equals positive K. And this is one way you can determine the order of your reaction experimentally. So let's do this. So we have a reaction here. I'm happening to use a reaction that has pressure instead of concentration, but it would work either way. And let's determine the order graphically. So will you plot the concentration or the pressure versus time? For this reaction, it's not linear. So this tells us this reaction is not zero order. All right. What if we plot the natural log of pressure as a function of time? Well, cool. This is the same thing as plotting concentration versus time. And for this reaction, we don't get a straight line either. So that means this is not first order. And in this class, we only give you 3 options, 0, 1, or 2. So that means it has to be second order. Then it turns out we plot 1 over pressure, the same idea as plotting 1 over concentration. And this gives us a straight line. Awesome. Now the slope here is equal to the rate constant. So the slope is 0.0002. So that would be our rate constant here. Awesome. Now let's talk about half-life. And so the half-life is defined as the time for a concentration of a reactant to decrease to half of what you started with. And you can just plug into the integrated rate law a concentration at some time that's equal to half your initial and solve those equations, rearrange, etc. And when you do that, you get these equations for second order and zero order. Now it depends on the rate constant, which is the same as it did for first order when we did this earlier. But new for second and zero order is that it also depends on the concentration. Just the nature of the reactions, your half-life depends on the concentration that you have. And so this is not as useful of a description of the reaction, so we tend to not talk about second order and zero order reactions in terms of half-life. But you easily could, and just use this equation, and then it would work out just fine. And that's all I have for this video. Thanks for watching.